All right, hello and good afternoon and welcome. Otherwise known as good welcome. Holy moly, I'm making up all sorts of words that don't even exist today. Welcome to Monday's lecture. We had a gap. Wednesday was Veterans Day. So, we had a little bit of time off, which was hopefully nice for you. For me, it was good getting caught up on some things, and yeah, good afternoon, Kate. Shoot, it's Monday. I hope everyone is having a solid Monday. So, we're gonna keep. Pressing on through chapter 9. Let's see. I saved. There we go. So I left off on Monday, not Wednesday, last Monday, with a few examples to try on your own, and so we're going to pick up with those. Finish Lewis structures, and yeah, we'll see. We might finish Lewis structures today. If not, we'll wrap it up on Wednesday. So this is just by way of reminder. We are going to be, these are the steps for drawing Lewis structures, and we have been focusing on locking down 1 through 4. And after we complete the octets, we're done. Today, we're going to learn about assigning formal charge and resonance structure. So we're going to be diving into some new territory there. Let's go ahead and start with drawing some Lewis structures. And I'm going to lead off with nitrogen gas, N2. All right. Now, step number 1 is we need to know what our total number of valence electrons are. And for nitrogen has 5 valence electrons. Whoops. So, because we have 2 nitrogens in our molecule, that means we have 10 electrons to spend in our budget total. We've got 10 electrons with which we can draw our Lewis structure. Now, so that's our total valence electrons. We don't really need to worry about selecting a central atom for this molecule because there's only 2 atoms present. So we start by making a bond between our 2 nitrogens, and as we know, each bond holds 2 electrons, and so we spend 2 electrons from our budget to bond our 2 nitrogens together. Now, we know that every element wants 8 electrons, right? That is the octet rule. And so our first nitrogen, doesn't matter which one you pick, I'm going to go with the one on the left. It right now has access to 2 electrons. It wants a total of 8, so we're going to complete its octet by giving it 1, 2, 3, 4, 5, 6 electrons in lone pairs. All right, 3 lone pairs, 6 electrons. That leaves 2 electrons in our budget. So the nitrogen on the left has a full octet. The nitrogen on the right has access to 2 electrons. It wants 8, but unfortunately there are only 2 electrons left in the budget, so we can only afford to give this nitrogen 1 lone pair. All right. Now, when you look at this nitrogen, it has 2 electrons in the bond plus 2 electrons in its lone pairs, but we know it wants 8, right? We are quote unquote missing 4 electrons. All right. On last lecture on Monday, we talked about how when you're missing 2 electrons, then you take a lone pair off of the atom with a full octet, and you turn that lone pair into a double bond, right? So if you look at, for example, if you look at this nitrogen, it has 2 electrons in its bond, plus 6 electrons worth of lone pairs, all right? So it has a full octet. Our nitrogen on the right does not have a full octet. So what we do is you take 2 electrons away and use it to make a double bond between the 2 nuclei. You'll notice that the nitrogen on the left still has access to 8 electrons. 2, 4 in the bond, right? And then 4 in lone pairs. Now the nitrogen on the right has access to 4 electrons. 2 green, 2 blue, 2 salmon. It still doesn't have 8 though, right? When we're missing 2, we made a double bond. Here we were missing 4. So we are going to do the exact same thing a second time. We take a lone pair from the nitrogen with a full octet and use it to make a multiple bond. Now the nitrogen on the right has access to 8 electrons. Now our octets are complete. So this is the Lewis structure for N2. And the type of bond that exists between the 2 nitrogen atoms, this is called a triple bond. All right, so we saw a double bond at the end of lecture on Monday, and now this is a triple bond. This is going to be a very common theme. Whenever you are 2 electrons short, you're going to need to make a double bond in your molecule. Whenever you are 4 electrons short, it could be a triple, could be 2 doubles. We'll see. It depends upon the molecule. All right, so this is our first exposure to a triple bond. All right, I'm going to do a couple more examples to kind of warm us up. Let's go ahead and do the Lewis structure for formaldehyde, whose chemical formula is CH2O. That's the Lewis structure or the molecular formula for formaldehyde. So carbon has 4 valence electrons. Oxygen has 6. Again, we're getting these numbers from the periodic table and the column that each element falls in. Hydrogen only has 1 electron, but we've got 2 of them, so we got to multiply that by 2. So now, let's see, we've got 12 electrons in our budget. So we have our total number of valence electrons. Next, we need to select our central atom, and we said for your central atom, you want to select the element that likes to make the most bonds. And we said to do that, we can determine that by looking at our Lewis dot structures. All right. And the number of unpaired electrons tells you how many bonds each element likes to make. So hydrogen will normally make 1 bond. It likes 1 bond. Carbon likes 4 bonds. Oxygen, because it has 2 unpaired electrons, likes 2 bonds. So because carbon likes to make the greatest number of bonds, we're going to select carbon for our central atom. All right, so we're going to put carbon in the middle. Next, we need to attach all atoms to our central atom. So, we need to throw an oxygen on here and 2 hydrogens. All right, this is going to take, so if we're making 3 bonds, that is going to cost us half of our budget, 6 electrons. So we have 6 electrons remaining. Now, we've got to complete our octets. Each hydrogen is totally satisfied, right? It only wants to have 2 electrons because its nearest noble gas is helium. But oxygen and carbon still have needs, right? If you look at oxygen, right now, oxygen has access to 2 electrons. It needs 8. So we're going to add 1, 2, 3, 4, 5, 6 electrons in the form of lone pairs. That is going to bottom out our budget. We have no more electrons to spend. The problem lies in carbon, all right? If you look, carbon has access to 6 electrons, right? And it's 3 bonds, but it needs 8. Trouble is, we're out of electrons, but at this point, we're not phased, right? We're not phased by this. We know what we need to do is take a lone pair off of oxygen and use it to form a double bond. Now carbon has access to 8 electrons and oxygen still has access to 8. So this is the Lewis structure for formaldehyde. All right. Now, let's see. Okay. So at this point in time, oh, well, I guess we finished this problem. Complete octets, attached all the atoms to the central. We have our Lewis structure. All right, at this point in time, I wrote up a couple more examples in our last class. And if you want to see them, hit me up in office hours tonight. I'd be more than happy to go over them with you. But we're going to move on just because we have some significant ground to cover before we can put Lewis structures finally to bed. All right. And as you may suspect, we are going to hit up we're going to discuss assigning formal charges and resonance structures. But before we do, we actually need to revisit number 4, completing octets, because, oh, let's see. Okay, so we've been up to this moment in time living and dying by the octet rule, right? It's everything has to have a complete octet. And we've been very, very octet rule focused. Before we move on to assigning formal charges and talking about resonance structures, we need to talk about when it's okay to break the octet rule. All right, we need to discuss breaking the octet rule. All right. There is one element on the periodic table that that kind of marches to the beat of its own drum. And you should just be aware of this. So first, we should just talk about boron. Emma, that is a great question. Emma, that is a great question. So Emma just asked, we saw a triple bond in lecture. Is it possible for there to be a quad bond between two atoms? And the answer is quadruple bonds have been demonstrated to exist, but not for main group elements. They have been documented in nature, but only between very specific transition metal compounds. So the thing is, are they out there? Yes, but you don't see them in the main group, and so you will not see them in this class. Triple bond is the highest bond order that you'll see kind of in normal chemistry. There are some very interesting examples out there of bond orders higher than 3, though. So they can exist, but you won't see them in this class, and I won't test you on them. And if you want to see more of that, go take inorganic chemistry, which is not general chemistry. Inorganic chemistry is an upper division chemistry class, and it is awesome. So go out there, find it once you pass this class. Okay, so let's talk about breaking the octet rule. We're going to start with boron. Boron is a very weird element. It is located on the periodic table right... where are you? Here you are, right here. And boron, if you look at its Lewis dot structure, has 3 unpaired electrons. Emma, it is super cool. It's honestly, it's some of the coolest, in my opinion, some of the coolest chemistry out there. With the transition metals is the higher bond order stuff. But anyways, so boron has 3 dots, which 3 unpaired electrons, which tells us that it kind of likes to make 3 bonds, right? 3 unpaired electrons means it likes to make 3 bonds. And the thing about boron is that boron can have 6 or 8 electrons in its valence. So boron, there are Lewis structures of boron that have 4 bonds. There are Lewis structures of boron that have 3 bonds, and either one is fine. Okay, so boron is the one exception where it's allowed to have less than 8 electrons. And the reason, if you look at it, boron is not a metal, right? So when you are wondering, why does it behave like this? It's not a metal, which means it won't lose its electrons. It's not going to lose electrons to drop down to helium's electron configuration. But at the same time, it's 1, 2, 3, 4, 5 electrons away from neon. It is not. It's not that electronegative. So it's hard for boron to gain extra electrons. So the thing is, it's not like boron would love to have 8 valence electrons, but because of its low electronegativity, it's hard for it to get extra electrons. So it just kind of has to be content with its subpar life of 6 valence electrons. Sometimes it gets 8, but sometimes it doesn't, and it can live with it. Okay, so that's the one, boron's the one example where you have fewer than 8 electrons in play. But what's far more common is what we call expanded octets. All right, when we talk about an expanded octet, we're talking about an element with more than 8 electrons in its valence. All right. Now, if you're wondering what elements are allowed to have an expanded octet, or which elements are allowed to have more than 8 electrons in their valence, the answer might shock you. All of these elements are allowed to have an expanded octet. These elements right here are all allowed to break the octet rule. And that might drop your jaw, because that's actually most of the periodic table. You might look at this and go, wait, you're telling me that the only elements that aren't allowed to break the octet rule is anything under atomic number 10? Because this thing goes up to, what's that, 119? So less than 10%, or over 90% are allowed to break the octet rule is what I'm telling you. And that is correct. More than 90% of the periodic table is allowed to break the octet rule. You may be wondering, well, why do we even teach the octet rule then, since nobody has to follow it, or almost no one has to follow it? And there's two answers to that. First, just because all of these elements shaded in green are allowed to break the octet rule doesn't mean they do, okay? These elements are capable of violating the octet rule, but they usually abide by it anyway, all right? So they're allowed to, but that doesn't mean they always do. They actually usually follow the octet rule. So that's one reason why it's useful. The second, so first off, just because an element is capable, or I should say can have, an expanded octet, does not mean it will. All right, so just because it can doesn't mean it will. The second reason why the octet rule is important is look at the elements that never violate the octet rule. Hydrogen, carbon, nitrogen, oxygen. All right. All biological systems are predominantly composed of elements are predominantly composed of elements that always follow the octet rule. That always follow the octet rule. So just because most of the periodic table is allowed to break it doesn't mean that most of our bodies are allowed to break it. The majority of the elements inside of us, inside all living systems, always follow the octet rule. So even if the majority of the periodic table can break it, the majority of our biological systems strictly abide by it. And if you can understand that, then that rule that governs them, you'll have a better insight into how the biomechanical processes within ourselves and other creatures function. So that's another reason why the octet rule is so important, is even though only 10 elements strictly adhere to it, not even boron, so less than 10, right? The elements that do, hydrogen, carbon, nitrogen, oxygen, that's almost all of us right there. So that is another reason why the octet rule is kind of given preeminence. But we should, I need to mention though for a minute why. I need to take a second to talk about why is it that on the third period, right, starting here on the third period, why are these elements allowed to break the octet rule? And to show you why, I want to take a look at chlorine. All right, so chlorine's right here. Let's go ahead and write its noble gas configuration. The noble gas configuration for chlorine starts with a neon core. All right, and then it's 3s2, 3p5. All right. Now, the reason why it starts here, the reason why it changes on the third period is because the third period is where a new subshell gets introduced, right? The D block. And chlorine has 2 electrons in its s orbital, in its s subshell, 3 electrons in its p subshell, and 0 electrons in its D subshell, right? Normally we don't write the subshells that carry no electrons, but I'm doing this for emphasis. Chlorine has d orbitals with no electrons in them. That is why it is able to hold more than 8 electrons in its valence. All right, chlorine has d orbitals with 0 electrons. That's why it's able to hold more than 8 electrons in its valence. The octet rule comes from the fact that there's 1 s orbital and 3 p orbitals. So you've got 4 orbitals, which can hold 8 electrons. Chlorine now has 5 empty orbitals, so it's able to hold much more. And that is true for every element on the third period and lower. They all have access to their d orbitals. And so that's what allows them to expand beyond 8 valence electrons. All right. Now, where this is going to change things for you is right here when it comes to picking your central atom. Or actually here. Yeah, Richard, that is a great analogy. Those d electrons, those empty d electrons, do kind of function like backup storage. It's not your main hard drive, it's not the drive that you're booting from, but if you need to, you can push some files, you can push some information to that backup storage drive, and you still have access to it, even though it's not the drive that you're booting from. That is an excellent analogy for what those d orbitals do for elements that expand beyond their the regular octet. So where this will affect how you draw Lewis structures will come in, it'll come into play right here when you're selecting a central atom. Elements that can have an expanded octet are able to form more bonds than those that cannot. And so you want to keep that in mind when it comes to selecting your central atom. All right, they're able to form more bonds than those elements that can't, and so they become the best candidates for central atoms when you're developing your Lewis structures. All right, now we're going to use these, but before we do, we need to talk about formal charges. All right, we need to dig into formal charges, and then we'll be able to use this information about expanded octets. All right. Okay. Let's get into this. Up to this moment in time, every Lewis structure that we've drawn has been neutral. All right. They've all been neutral. They haven't had any charges. So we haven't had to worry about formal charges. Now it's time. The time has come to cross that Rubicon. So let's draw the Lewis structure for the following element, or not element, molecule. Let's draw the Lewis structure for hydroxide. All right. The first place so you'll notice instantly right off the bat that we have a negative charge. This is an ion. All right. So the first place that this will affect us is when we do step 1, when we total our valence electrons. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron. All right, but now, what does that negative charge mean? When an ion has a charge of -1, that means there is 1 extra electron. All right, there's 1 extra electron. So if you have a charge of -1, you need to add an additional electron to your budget. So we have 8 electrons to spend. All right, we don't have a central atom here because there's only 2 atoms to attach, but we need to attach them. Right at this point in time, we've totaled our valence electrons. We don't have to worry about our central atom, but attaching these 2 is going to cost us 2 electrons, leaving us with 6. All right. Now we've done steps 1 through 3. We need to complete our octets. Hydrogen is totally fine. It has access to 2 electrons, which is what it wants because its nearest noble gas is helium. Oxygen, on the other hand, needs 8 valence electrons, and we have 6 electrons left in our budget. So we spend them to complete oxygen's octet. Now it has access to 8. Hydrogen has access to 8. So we've done steps 1 through 4, but now we have to address and deal with these last 2. We need to assign formal charges. And actually, let me redo that. We're not going to worry about resonance structures just yet. First, we have to worry about assigning our formal charges. All right. Now, here's the thing. We're going to come back to this slide. But before we do, we need to spend a minute to talk about what formal charge is. All right. So formal charge tells you which elements in a Lewis structure have more, or I should say, which elements in a Lewis structure are electron rich because they're negative, and which elements are electron poor. Because they are positive. If any of you have aspirations of taking organic chemistry, which is the single coolest class offered at FLC, if I can plug it shamelessly, this will be hugely important, your ability to identify electron-rich and electron-poor elements within a molecule. All right. Formal charges tell you which elements in a Lewis structure have more electrons than they should, because they will have negative formal charges, and which elements in a Lewis structure have less electrons than they should, because they will have a positive formal charge. Now, the equation for calculating formal charge is equal to, you take the number of electrons I should say the number of valence electrons for the neutral elements and you subtract the number of valence electrons in the Lewis structure. All right? You take the number of valence electrons for the neutral element and subtract the number of valence electrons for the Lewis structure. So if we're going to take the Lewis structure for hydroxide that we've drawn, we need to assign a formal charge for each. Let's do Hang on. We need to talk real quick about this. All right. the number for calculating the valence electrons for that element in the Lewis structure, this equals, you get 1 electron per bond plus all lone pair electrons. All right, when you're calculating how many electrons an element has in a Lewis structure, you count 1 electron per bond and then all the lone pair electrons. So when you look at hydroxide now, let's do hydrogen first. Hydrogen has, when it's neutral, the valence electrons for the neutral element, hydrogen, when it's neutral, has 1 valence electron. And then we go minus, right, the number of electrons in the Lewis structure. Well, we get 1 electron per bond. Hydrogen only has 1 bond and no lone pairs. So 1 minus 1 gives us a formal charge of 0. And when your element has a formal charge of 0, you don't write any number, all right? You only write formal charges that are greater than or less than 0. But hydrogen has a formal charge of 0. So we don't write anything there. Now let's take a look at oxygen. Oxygen, when it is neutral, has 6 valence electrons. Now, in this Lewis structure, we have 1 electron, because we have 1 bond, plus 1, 2, 3, 4, 5, 6 electrons in lone pairs. So we have 6 minus 7, which gives us a formal charge here for oxygen of -1. And because we have a formal charge of -1, we write that kind of next to the element off to the side, kind of superscripted. So this is the Lewis structure for hydroxide. If we dial all the way back to our original problem, then it would have a negative charge floating next to the oxygen, and this is the formal charge. Again, we're not quite at dealing with resonance structures yet, so we're going to put that off for a little while longer, but this is the Lewis structure with the formal charges. Now, something that I want to note, in the past, you may have dealt with, so this is the Lewis structure for for hydroxide. You may have been taught in the past that when you have a formal charge, what you do is you draw the Lewis structure, and then once you're finished, you put a bracket around it with the charge outside of the bracket. All right. This right here is also correct. So you can do it that way, and it is 100% correct. There's a warning, though. In order to determine the best resonance structure, all right, in order to determine the best resonance structure, you need to be able to assign formal charges. So you can totally use the bracket method for writing Lewis structure, throw the charge outside. But if you do not know how to assign formal charges, you won't be able to do step 6, which is figuring out your best resonance structure. And if you can't do that, then you're going to get those answers incorrect. So you can totally slap a bracket around it with the charge outside. That's correct. As long as the best resonance structure is inside the bracket. Now, we haven't talked about what that is. We will very soon. But I just wanted to say, like, oftentimes students hear me after teaching them how to do formal charge here, oh, you can just put a bracket around it, and they think, oh, sweet, I don't need to know that. You totally do. You totally do need to know how to assign formal charges because it'll become important when we start discussing resonance structures. All right, but you're also allowed to draw, use the bracket notation as long as the best resonance structure is on the inside of that bracket. Okay, so just keep that in mind and proceed with caution. Let's do another example where we are where we have to deal with formal charge but don't quite have resonance structures in play yet. Let's write the draw the Lewis structure for ammonium. All right, NH4 plus. With hydroxide, we saw how to deal with an ion with a negative charge. Now let's look at how we deal with a positive charge. All right, step number 1, we have to total our number of electrons. Nitrogen has 4 valence electrons. Hydrogen has 1 valence electron, but since we have 4 in play, all of our hydrogens together will bring 4. Now, how do we deal with this positive charge? Well, if you have a charge of positive 1, that means you have 1 fewer electrons than you should have in the structure. You're essentially missing 1. So for every positive charge you have, you need to subtract 1 electron from your total count. So our budget here will actually be 7 valence electrons. No, it won't. Sorry, nitrogen does not have 4 valence electrons. If you look at the periodic table, it has 5. So 5 plus 4 is 9, minus 1 is 8. We have 8 valence electrons. Now, let's attach, so we've totaled our valence electrons. Nitrogen can make more bonds than hydrogen. That's our central atom. Let's attach all of our hydrogens to our central. This will take, so we need to make 4 bonds. This will cost 2, 4, 6, 8. That totals out our electron budget, right? We have no electrons left to spend. And now we need to complete our octets. One thing you'll notice is that everybody has a full octet. Each hydrogen has access to 2 electrons in the 1 single bond. Nitrogen, the central atom, has 4 single bonds, 2 electrons per. That's access to 8. So our octets are actually complete. Now let's assign formal charges. So looking at hydrogen, when hydrogen is neutral, it has a formal charge, or it has 1 valence electron. In this structure, it has 1 bond and 0 lone pairs, and we know when we calculate formal charges, you count 1 electron per bond. So 1 minus 1 is 0. Hydrogen has a formal charge of 0, and you'll notice that every hydrogen in this molecule, when you calculate the formal charge, will come out with a formal charge of 0. Let's take a look at nitrogen. All right, nitrogen, when it's neutral, has 5 valence electrons. In this structure, when you calculate formal charges, you get, each element gets 1 electron per bond. There's 4 bonds, so that's 4 electrons, plus the number of electrons in lone pairs. In this structure, nitrogen has no lone pairs, so we go 5 minus 4 is positive 1. All right, so nitrogen has a formal charge of positive 1. We put that positive charge right next to nitrogen in the structure, and this is the Lewis structure for ammonium. All right. Now, let's take this up a notch. Let's draw the Lewis structure for nitrate. Let's draw the Lewis structure for nitrate. Now, nitrogen has 5 valence electrons. All right. Oxygen has 6, but we have 3 of them. So 3 times 6 is 18. And then we have our negative charge, right? We have a charge of negative 1, which means we have 1 more electron than we should have. So it adds 1 to our total budget. Now, when you add all these together, you end up with 24 electrons, right? 24 valence electrons. We're going to select nitrogen as our central atom because it likes to make 3 bonds. Oxygen likes to make 2, so you roll with the one that likes to make more. Step number 2, we need to attach all of our atoms to our central atom. This is going to cost us 2, 4, 6 electrons. Leaving us with 18. All right, next we got to complete our octets. And you'll notice that, for example, this oxygen has 2 electrons. It needs 6. So we need to give it 6 more electrons. And that's actually the case for all of these oxygens. Each oxygen has access to 2 electrons. It needs 6 more. So we've got 3 oxygens that need 6 electrons. 3 times 6 is 18, and that turns out to be the remainder of our budget. We have just enough to give every oxygen in this molecule a full octet. Every oxygen has a full octet, but nitrogen is still out in the cold. You'll notice that for nitrogen, it has access to 6 electrons. It needs 8, so we need to take 2 of our electrons off of an oxygen, doesn't matter which one. Turn that into a double. And now, nitrogen has 8 valence electrons. All right, so we have selected our central atom, attached all others, completed octets. Now we need to assign formal charges. All right. We need to assign formal charges to every element in this molecule. Let's go ahead and start with this oxygen right here. Now, neutral oxygen has 6 valence electrons. In this molecule, right, so we take the valence electrons for the neutral element and subtract how many valence electrons it has in this molecule. We get 1 electron per bond, so we've got 2 bonds, 1, 2, plus 4 lone pairs. So we've got 2 electrons in bonds, 4 electrons in lone pairs. So this comes out to be a formal charge of 0 for this oxygen. Let's take a look at this oxygen. 6 valence electrons, because that's true for all oxygens. Now, minus, we have one bond, so we get 1 electron per bond, plus we have 6 electrons in lone pairs. So this oxygen actually has a formal charge of -1, because 6 minus 7 is -1. You'll notice that when you add up, when you calculate the formal charge for this third oxygen, it comes out to be the same, -1. And now let's look at our formal charge for nitrogen. Nitrogen, when it is neutral, has 5 valence electrons. In this structure, we have 0 electrons in lone pairs, but we do have 4 bonds, right? So we have 5 minus 4 equals +1. So we put a positive formal charge by our central nitrogen. All right. Now, this is, then the Lewis structure for nitrate. And I want to point something out. In the previous 2 examples that we did, there was only 1 negative charge on the entire ion, right? And then in the Lewis structures, there was only 1 charge. Ammonium only had a +1. Hydroxide only had a -1. Here, nitrate has a charge of -1, right? Overall charge of -1. But the formal charges, it has 2 -1s and a +1. So you actually have more formal charges than you do total charge, but you'll notice that when you add all your formal charges together, they equal your total charge, and that will always be true. All right, total charge the total charge of an ion is always equal to the sum of all formal charges. All right, so don't freak out if you have more formal charges than your total charge, but they must always, the sum of all your formal charges must always equal the total charge on your species. Cool? All right. Also, don't make the mistake of thinking that, oh, there's a total charge of -1, therefore there can only be 1 charge in the molecule. That is not the case, as we see here. All right, now I'm going to pause for a minute, and kind of explore something with you. I want to go back to that moment when we were drawing the Lewis structure for nitrate, and we had spent all our electrons. So we had everything here, right? Oops. Sorry, hang on. There we go. All right. At this moment in time, I said, so we had spent all our electrons, right? We needed to fill nitrogen's octet. And we did that by removing 2 electrons from one of our oxygen and using it to make a double bond, right? And I did that with the one that was on the right-hand side, right? The rightmost oxygen. But my question for you is, what would have happened if I had done the exact same thing just for the oxygen that was on the very left? What if I had decided to take my 2 electrons from that oxygen? instead? Right, what if I had stolen them from right here, made a double bond like so? Or there's a third door. I could have, while drawing the Lewis structure, just as easily taken the 2 electrons for the double bond from the oxygen that was pointing directly down. Which, if I had, would have given me a Lewis structure that looks like this. All right. Once I throw my formal charges on there, they all come out to look like this. And at the time when I was grabbing a lone pair to make a double bond, I said, oh, it doesn't matter, just pick one, right? But when you look at these 3 structures, though they're undoubtedly similar, are distinctly different. And it raises the question, which one is the true structure? Is it the one with the double bond to the right? Is it double bond to the left? Is it double bond straight down? Which oxygen has the double bond? Which structure, which Lewis structure reflects the true structure of the molecule? And the answer to that question, which one is the real structure, is none of them and all of them. None of these individual structures are the true structure of nitrate, and all of them together are the true structure, is the true structure of nitrate. All right, what am I saying? It sounds like I'm talking out of both sides of my mouth. These 3 Lewis structures right here are all Lewis structures of the same molecule, and they have a very special relationship. These are called resonance structures. All right, these are called resonance structures. And the relationship of these resonance structures to the true structure of the molecule is something that is very, very, very unique. All right. We say that the true structure of a molecule is the superposition of all the molecule's resonance structures. All right, the true structure of the molecule is the superposition of all of the molecule's resonance structures, and the true structure most resembles most resembles the best resonance structure? All right. So, okay, what are we talking about? What is this enigmatic word superposition? All right, superposition is a word that basically means it's a combination of all of these together. All of these structures together are the superposition. The superposition is all of these kind of overlaid together and combined together. All right. So one way to think about resonance structures is like this. I could show you my my right profile. Take a picture. I could show you my left profile. You can take another picture. And if I held up the two pictures of my profiles and asked you which one was me, you would laugh because it's a silly question. It's not that one is me and one's not, but I am both of them, right? I am the superposition of my right and left profile together, all right? That is what the actual structure of a molecule is in relationship to its resonance structures. The way to think about the resonance structures is they are snapshots, individual photos of a molecule almost from different perspectives. But the true structure of the molecule is all of those things combined, just like I am the combination of both my right and left profiles. All right. That is the way you want to think about these resonance structures. So when I say here we have three different resonance structures, which is the real structure? Is there a double bond between to the right, to the left, or pointing straight down? The answer is there's a double bond in neither of those places and all of those places. All right. In the true structure. Oh, hang on. I'm going to have to clear this the old-fashioned way. All right. So in the true structure for nitrate, the nitrogen-oxygen bond in nitrate is longer than a normal nitrogen-oxygen double bond and shorter than a normal nitrogen-oxygen single bond. All right, it is in between the normal double bond length and single bond length. That's because the NO bonds in nitrate are partial single and double bonds. All right. The true structure is in between the truth of the individual snapshots that we see in the Lewis structure. All right. So that is the information that resonance structures communicate, and that's kind of what they are. Again, if you are going to go on and take organic chemistry, you're going to spend a ton of time talking about resonance structures, discussing resonance structures, diving into all of that. rich information. All right. Now, let's stop for a minute and talk about how do we find the Lewis structure that is the best resonance structure. All right. Because when you are asked to draw Lewis structures, you'll be asked draw the best resonance structure for this molecule. All right. And the best resonance structure has these things will be true of the best resonance structure. All right. In the best resonance structure, first, you want to make sure that you complete all octets. All right. If the octets aren't complete, you do not have the best resonance structure. All right, and that is the most important one. Second order of importance, you need to minimize formal charges. All right, now you have learned how to assign formal charges, but you're like, I thought they were just there. What do you mean minimize them? We'll do an example and you'll see what I'm talking about. And then the third thing to keep in mind when you are checking to see if the structure you have is the best resonance structure, the first two will be true, and then this will also be true. Given a choice, and you'll see what I mean by given a choice once we start doing examples. Given a choice, negative formal charges should be placed on more electronegative elements. Oh, running out of space there. And more electronegative elements. All right. These are the three things that you want to analyze for when determining the best resonance structure for your molecule. Let's put this into practice. Let's draw the Lewis structure for let's do let's draw the Lewis structure for, how about ClO2, chloride. All right. Let's begin by totaling our electrons, right? So chlorine has 7 valence electrons. Oxygen has 6, but we have 2 of them. So we're rolling in with 12, and then our negative charge means there's 1 extra electron in play. So we have 20 electrons to choose from. Now, when it comes to selecting our central atom, we're going to pick chlorine as our central atom because it's on the third period, right? We said that third period elements can have expanded octets. And so we'll select chlorine to be our central atom. Next, we need to attach our other atoms to our central. To make 2 bonds will cost 4 electrons. So we lose 4 electrons or spend 4 electrons out of our budget, leaving us with 16. All right. Next, we need to fill our octets. You'll notice that this oxygen has 2. It needs 8. So let's go ahead and spend 6 electrons on the rightmost oxygen to fill out its octet. Let's spend another 6 on the leftmost oxygen to fill out its octet. Leaving us with 4. All right, now chlorine has access to 4 electrons right now. All right, and it needs a total of 8. And check this out, we have 4 electrons in our budget, so we can actually give chlorine the number of valence electrons it needs. All right, so at this point in time, we have finished the first 4 steps of drawing a Lewis structure, central atom, attached the other atoms, filled out our octets. Now we need to calculate our formal charges. And this is where, if you're just a person who likes to throw brackets and move on, this is where you'll get the problem wrong. All right. So let's calculate, our formal charges. All right. First, for this oxygen, when oxygen is neutral, it has 6 valence electrons. When you're calculating formal charges, you count 1 electron per bond. So this oxygen has 1 bond. And then you count the total number of lone pairs. So it has 6 lone pairs. 1 plus 6 is 7. So 6 minus 7 gives us a formal charge of -1 for this oxygen. Let's look at chlorine. Chlorine, when it's neutral, has 7 valence electrons in the structure. Formal charge calculation, you get 1 electron per bond. We've got 2 bonds, so that's 2. Plus another 4, right, in lone pairs. So 7 minus 6 is a +1. So our chlorine in the center has a formal charge of +1. And then the oxygen on the end, oxygen has 6 valence electrons in the structure. It has 1 electron in a bond, plus another 6 in lone pairs. So 6 minus 7 is -1. All right. Now, oops. Here. I'm going to redraw the structure really quick that we just had. So you have chlorine, single bonded to 2 oxygens, each with 3 lone pairs. Chlorine has 2 lone pairs. Chlorine has a formal charge of +1. Each oxygen has a formal charge of -1. All right, now, so those are our formal charges. Now, you may be wondering, how do I know whether or not my formal charges can be minimized? All right, and the answer to that question is you can draw a better resonance structure. You can minimize your formal charges if you have a formal negative on an atom next to another atom with a formal positive, only if this is a 3rd period element or lower. If it's lower than the 3rd period, it'll work too. If that element bearing the positive charge is on the 3rd period or lower, then you can minimize your formal charges. All right, here's how. Take the electron, 1 lone pair, on your element with the negative charge and turn it into a multiple bond between the oxygen and the chlorine. Now, I want to pause for a minute here. Well, actually, hang on before I do that. let me draw that structure. So this oxygen's unaffected. We haven't messed with its electrons, so it'll have the same formal. But now let's assign, well, formal charges to chlorine and oxygen here. All right. So let's look. Chlorine. So I took that lone pair, turned it into a double bond. Watch what happens to the formal charges. For chlorine, as we know, has 7 valence electrons when it's neutral. In this structure, you get 1 electron per bond when you're calculating formal charges. So there's 3 bonds, chlorine has 3, plus the electrons it has as lone pairs, 3 plus 4 is 7. So chlorine has a formal charge of 0. What about oxygen? Well, when oxygen's neutral, it has 6. As drawn in this structure, this oxygen has 2 electrons in bonds, right? 2 bonds, 1 per, plus 4 in lone pairs, so 6 minus 6 is 0. So chlorine has a formal charge of 0, and this oxygen has a formal charge of 0. So you can see that formal charges are minimized. Whoa. All right, formal charges are minimized. We went from having 3 formal charges in our molecule to down to just having 1. And there's no way you can get rid of this one because you're dealing with an ion. You will always have at least a formal charge of -1. All right? Now, once students learn about this, they might go, well, shoot, that's kind of cool. Why don't I do it again? What's stopping me from taking this lone pair and making a double bond there? Well, nothing. Nothing's stopping you. Let's see what happens when we do. First off, this oxygen that's way out to the very right will not experience any change in formal charge because none of its electrons change. It's the same in both. Now let's go ahead and look at what happens to oxygen, the oxygen on the left, and chlorine. First, oxygen has 6 valence electrons. In this Lewis structure as drawn, it has 2 bonds, so 1 per bond, plus its 4 lone pairs, 6 minus 6, formal charge of 0. Let's look at chlorine. Chlorine has 7 valence electrons when it's neutral. In this Lewis structure, it has 1 electron per bond and it has 4 bonds, plus another 4 in lone pairs. 7 minus 8 is -1. So in this Lewis structure, chlorine in the center has a formal charge of -1, and each oxygen out on the side is neutral. So we have 3 Lewis structures each, and we have to select which one is the best resonance structure. Well, the one way out on the end, this one is not the best resonance structure because formal charges are not minimized. Right? You've got 3 formal charges. The other 2, though, each only have 1. So which one is better? And the answer is the one in the center. This one is the best resonance structure because oxygen is more electronegative than chlorine. Oxygen is more electronegative than chlorine, and we'd rather put a negative formal charge on a more electronegative element than a less electronegative element because the more electronegative element wants it more. All right, so that is the best resonance structure. Now, one last thing that I want to point out here, then we'll call it a day, is I want to draw some special attention to these arrows. All right, these are called resonance arrows. They're never used for reactions. They're only used for resonance structures, all right? A resonance arrow is one line with an arrowhead on either side, all right? This is not to be confused with an equilibrium arrow, which is two arrows, one pointing forward and one pointing back. Sometimes equilibrium arrows are also written like this. These are not resonance arrows, all right? These are called equilibrium arrows. All right, but a resonance arrow looks like that. One line, an arrowhead on either side, all right? You should know that in my class and also in other classes, if you draw an equilibrium arrow when you're doing resonance structures, you get points docked. If you draw a resonance arrow when you mean equilibrium arrows, and that'll come into play when you take 401. If I were teaching it, you would also get points docked. Different professors may have different policies, so it's totally up to them, but you should know that there is a difference. Resonance arrows, one line, two arrowheads. Equilibrium arrows, two different arrows, one pointing forward, one pointing backward. Cool? I wanted to stress that so that you'd all get it straight in your futures. All right, we went maybe a little bit over today, but we'll pick up with more Lewis structures examples of more Lewis structures on Wednesday. We'll do more examples of violating the octet rule, more examples where we're minimizing formal charge, etc., and more examples where we're going for the best resonance structure. And depending upon how Wednesday goes, we'll most likely strike out into our lecture on Vesper, on molecular geometries. But how deep into that depends upon how Wednesday goes. Anyways, thank you all so much. If I don't see you tonight in office hours, I will see you Tuesday in the lecture.